All right, guys, so the title of this lesson is the Pythagorean Theorem, which many of you may already be familiar with. Whether you are or are not, I'd like you to complete this exercise in explaining where it comes from and why it exists. So, what we have here are four identical copies of the triangle below. All right, so this triangle here has been copied, and there are now four of them, and we're using these triangles to put them in place and create this figure here. And what you're going to find about this figure here is that because these four triangles are all exactly the same, we can easily figure out the area of this square, but we're just not going to know what that value is in terms of a real number. We're just going to have an expression in terms of A's, B's, and C's. So if these are, in fact, all the same triangle, then these hypotenuses must all, I guess I'm assuming that they're hypotenuses, but they are all right triangles. These hypotenuses must all have a measure of C. And these sides here must all be a length of B, and these sides are all a length of A. And so what that translates to over here in our diagram is an A here, here, and here, a B here, here, and here, and then C's in here. Okay, so there are two different ways that we can calculate the area of this square. Area 1 is, let's take the length of this square and multiply it by the width of this square. So that's going to be the first way that we calculate this. Since it's a square, its length is the same exact thing as its width. So we have a length of A plus B, whatever those values are, and we have a width of A plus B, whatever those values are. So the area here then is going to be A plus B times itself. Okay, let's make this look a little nicer. So I can go ahead and distribute the A's. Then I have an AB. Now I have another AB. And then I have a B squared. And finally, I can combine these two like terms. So I can rewrite this as A squared plus 2AB plus B squared. So this is one way that I can calculate the area of this figure. It's a square. The other way is I could go piece by piece and calculate the area of each of these individual slices and then add them all together. So I have four of these triangles, and the area of one triangle is 1/2 of the base times the height. So that's the area of just one of these. But I've got four of them. All right, plus, don't forget this figure on the inside, this thing here, is a square in itself. So I'm going to have to add the area of that. C times C, length times width. All right, so let's rewrite this a little bit nicer. So 4 times 1/2 is 2, and C times C is C squared. So now I've got two different ways to represent the area of this figure. Now remember, it's the same figure. So this must be the same area as this, because they are the same square. We've just calculated them different ways. So we're going to then say that the first area has to be equal to the second area, which means that A squared plus 2AB plus B squared has to equal 2 times the base times the height plus C squared. Now, one thing that I want to change here about the second area is, what are the base and the height of these triangles? Well, the base is B and the height is A. So another way that I could write that then is 2 times AB. So these two things have to be equal because they're just two different versions of the exact same area. And so if they must be equal, then this equation is true. And I'm just going to simplify this by making it look a little bit nicer here. I'm going to go ahead and subtract a 2ab from both sides, which is actually going to result in those two things being canceled. And this is a formula that hopefully you've seen before. But now you can see that it actually must be true if we assume a couple of things in the first place. If we assume that this was a right triangle from the start, then a squared plus b squared must equal c squared. And that is the Pythagorean theorem. So now what we're going to see is why that can be useful. So if we're told that the legs of a right triangle, and I'm just going to sketch a little right triangle here, have measures of 9 and 12, and again, I know those are the 9 and the 12 and not that one because that side is called the hypotenuse, then what is the length of the hypotenuse? Well, the side we're missing here is C. And I know that because this is a right triangle, the Pythagorean theorem has to hold true. So if I replace A with 9 and I replace B with 12, then I'll be able to figure out what C is. I do have to finish solving this though, so 9 squared is 81, 12 squared is 144. I can combine those and I'll end up with, let's see, 225. And now we're just solving this equation like we've solved many equations in the past. Go ahead and take the square root of 225, which means 15 must be the length of the hypotenuse. All right, another example of how this can be applied. We are going fast here, but that's because this is a video that you can pause and rewatch, so feel free to pause it and go back and watch the examples or pause while I'm explaining. In a triangle, the length of the hypotenuse, now we're told that it has a hypotenuse, so that's how I know it must be a right triangle, because if it has a hypotenuse, it's gotta be a right triangle. The hypotenuse has a length of 12, and the length of one of the legs is 8, and I would like to know what is the measure of the other leg. Well, if a squared plus b squared equals c squared, which it does since this is a right triangle, then a squared plus 8 squared must equal 12 squared. So a squared plus 64 must equal 144. And if I subtract 64 from both sides, then I'll have that a squared must equal 80. And now when I take the square root of both sides, I'll have that a is equal to the square root of 80, but 80 is not a perfect square. So I've got to work on simplifying this a little bit. Are there any perfect squares that are factors of 80? And there are. 16 is the largest perfect square that's a factor of 80, so I can rewrite this as 4 radical 5. All right. And the last question at the bottom, I'm going to leave. I would like you to answer it, and we'll talk about this one at the beginning of class tomorrow. Okay? I'll be posting my key to the notes without this question in it so that you can do the practice problems and check your work to see if you're correct.